In this video, we're doing a practice exercise on active filters. We're given a design problem that says design an active RC low-pass filter with the following properties. So we have certain constraints that we need to build our design based on. The first constraint is the cutoff frequency, which is given by 1 kilohertz. FC is equal to 1 kilohertz. The gain is equal to 6. Finally, we're given the value of one of the resistors, which is R1, whose value is equal to 1 kilo ohm. In the lab, we learn two active RC circuits. The low-pass active circuit, active RC, low-pass, the low-pass active RC filter, and the high-pass active RC filter. Thus, we need to determine which one is the correct one for this specific problem. We're going to revise again the physical property of the capacitor that says that the capacitor acts as an open circuit in low frequency signal. So for example, for the circuit on the left-hand side, if Vn is a low frequency signal, that means the capacitor will act as an open circuit as if it is not there in the circuit schematic. So if we remove C, this will look like the inverter op-amp circuit under low frequency signals, which means this is the correct circuit design for the active low pass RC filter. Now that we know the circuit schematic for our design, we need to figure out the parameters values for our circuit. We're given the value of R1, and we need to find the missing parameters values for C and R2. There's two formulas that relate the parameters of an active RC filter. First one is R2, the value of R2, and how it is related to the cutoff frequency and the capacitor. And the second formula is the gain, which is provided by R2 over R1. Notice that the formula for R2, or the formula that relates R2 to the cutoff frequency and the capacitor, is the same for the low pass filter and the high pass filter, except that we will use the value of R that is directly connected to the capacitor. For example, in this case, we have a low pass filter in which R2 is the resistor that is connected to C. Therefore, this formula will give us the value of R2. And if we're dealing with a high pass RC active filter, then this formula will give us the value of R1. So it will be R1 is equal to 1 over 2 times pi times F times C. Now we have two equations and two unknowns, so that it's possible for us to figure out the values of the unknowns. So we're going to simply substitute the values of the parameters that we have into the formulas to figure out the value of R2, which is simply 6 kilo ohms, and we can use the first formula to figure out the value of the capacitance, which turns out to be 26.5 nanofarad. Remember not to confuse the conversion part during the calculation. For example, just we need to emphasize that what the nanofarad means, kilo ohms, micro, etc. And make sure you do the conversion correctly when you do the calculation. Now that we have the correct circuit and the complete design with the complete parameters, the next step is to simulate the circuit. We were given R1, which is 1 kilo ohm. We figured out R2 and C based on the constraint that is given, which is the gain and the cutoff frequency. We need to know that Vn must be an AC voltage, which makes sense because it's a filter circuit, which means it will filter out certain frequency range. So the input voltage must have some sort of a frequency value. Um, for the simulation type, when we simulate the circuit on Multisim, we're going to use, of course, AC sweep, because we learned that AC sweep will help us plot the frequency response of a filter. Or in other words, it will plot the magnitude as a function of frequency for any given circuit. A quick design verification tip. Remember that when you measure V out at the cutoff frequency, it must be equal to minus 3 decibel if the gain is 0, but it will always be the maximum gain minus 3 decibel. So the text that's there is will only apply to the case where the gain is 1 or unity gain. That means when you convert it in decimal, it's going to be decibel is going to be 0. So as a general rule, just always take the maximum gain, subtract 3 from it, and then that will give you the gain in decibel at the cutoff frequency. Or equivalently, you can always take the maximum V out value and divide by square root of 2 if you're dealing with linear scale, which is the case when you're doing practical experiments. We'll see that later on once we move on to simulation. Now, moving on to simulating the circuit. In Multisim, we'll first start by placing the components. I'm starting with the ground, and then I'm placing resistors. First resistor is R1, and then I'm clicking on duplicate to create R2. You can start by placing the components first and then changing their values, or do that right away as you place components. Here I'm starting by placing the components, rearranging them, and then connecting them. And then finally, I'll label the input and the output voltages, and then I'll start adjusting the values, and revising the circuit, and then click simulate. Here I'm placing an AC voltage for the input voltage, and then directly connecting it to the ground and to R1. The next step is to place the op-amp. I'm placing a virtual 3-terminal op-amp. Observe that in the design that I have created earlier, the non-inverting input is the input that is connected to the ground, and here it's located at the top. Therefore, I will double click the op-amp and then scroll down to symbol for me to be able to choose a symbol that better fits my design purpose. Notice what will happen to the op-amp. Now I have the non-inverting input located at the bottom. This way my circuit will look cleaner and it will make my connection easier. I duplicated the ground connection and connected it to the non-inverting input of the op-amp. Again, I'm rearranging components to complete my circuit connection. You can do that by simply dragging and dropping components. Now I'm connecting R2, which is the feedback resistor, and finally I will connect the capacitor. Remember to always revise your circuit, make sure that the values are correct and the circuit connection of Multisim matches that you're intending to do. Now the circuit is almost complete. I will now place a voltage probe at the output for me to be able to plot it. So this will be V out. You can simply label it on the right hand side of the window as V out under ID. Now what I will do is I will click VN or V1 and replace its name with VN. The next step is to make sure that the values are correct for my circuit. So I will change the value of R2 to 6 kilo ohms according to the calculated value in the previous slide. Now I will change the value of the capacitance to 26.5 nanofarad according to how I calculated it again. Now I can say that my circuit is complete. The only thing left for me is to simulate it and verify its accuracy. I will click on the arrow next to interactive and choose AC sweep. You can start by adjusting the settings. What I will do now is change the stop frequencies to between somewhere slightly bigger than the cutoff frequency. My cutoff frequency is 1 kilohertz, so a range between 1 hertz and 5 kilohertz is sufficient. Next, you can always change the vertical scale right away, or you can simply run the simulation and then do the settings later on. What I will do first is I will hide the phase. This way I will only plot the magnitude and examine it. Next, I will place a cursor at the x-axis and then place one of the cursors at the maximum value. Make sure that it reads the maximum. Now it's in linear scale, so it's almost 6 volts, which is true because my Vn is 1 volt, so it makes sense since I have a gain of 6, so V out is 6. I will change the vertical scale now to decibel. That means V out is now in decibel scale. So the maximum V out is 15.56 decibel. I will subtract 3 from that number and then move cursor 2 at there. So 15 minus 0.56, sorry, 15.56 minus 3 is almost equal to 12.6 decibel. So I'll place my second cursor there, and then we'll read the frequency at that voltage. So that'll be the minus 3 decibel point, or the cutoff frequency point. A screenshot of that is sufficient for the solution of this exercise. So I will stop here. You can zoom in, rearrange, but that will do it for this exercise. Thank you for watching. Please let me know if you have any question. You can always send me an email at alatia@auk.edu.kw.